that Albert Einstein himself called it spooky action at a distance. Spukhafte. Sounds like science fiction, doesn't it?
It really does. It challenges our everyday intuition about how the world works, fundamentally.
Exactly. And today, that's what we're diving into. Quantum entanglement. We've got a great stack of sources you sent over from the original papers that started the whole thing, right up to the latest in quantum computing.
Yeah, it's quite a journey, from a philosophical puzzle to a core resource for new tech.
Right. So our mission here is to pull out the key insights, give you a solid understanding of this, well, revolutionary concept, because this isn't just physics for physicists anymore.
No, definitely not. Understanding entanglement is becoming key to understanding the next wave of technology, computing, communication, even sensing.
Okay, let's unpack this. Let's figure out why this spooky idea is not just weird, but actually incredibly useful. We need to go back to 1935. Einstein, Podolsky, and Rosen EPR, they write this paper. They weren't trying to break quantum mechanics, were they? More like poke holes in it.
That's a good way to put it. They argued it was incomplete. They came up with this thought experiment, the EPR paradox. It involves two particles prepared together in a special linked state, then separated by a large distance.
And they had this concept, the EPR criterion of reality.
Exactly. It's quite clever. They said, look, if you can predict something about a system with certainty, without disturbing it, then that property must be real. It must pre-exist your measurement.
Okay.
And for their entangled particles, they showed you could do this. Measure the momentum of particle A, and you instantly know the momentum of particle B, no matter how far away. Same for position.
But wait, Heisenberg's uncertainty principle says you can't know both position and momentum perfectly for one particle at the same time.
Precisely. That's the paradox. So EPR said, either quantum mechanics is missing something, these hidden variables that secretly determine the outcomes beforehand.
Or the spooky part. Measuring one particle instantly influences the other one across space. Non-locality.
And that was Einstein's big problem. Instantaneous influence. It seemed to completely violate his theory of relativity, the universe's speed limit, the speed of light. Nothing should go faster.
So that's where spooky action at a distance comes from. It was really about this non-locality clashing with relativity.
Yes, specifically the apparent instantaneous collapse of the wave function. You measure one, poof, the other one instantly knows its state. That's what felt spooky, suggesting faster than light influence.
Okay, but does it actually allow faster than light communication? Can we build an Ansible like in sci-fi?
The million-dollar question.
Yeah.
But the answer, according to the no communication theorem, is no. The correlations are instant, yes, but you can't use them to send a deliberate message faster than light.
How does that work?
Well, if Alice measures her particle, the outcome she gets is still random. Bob, measuring his, also gets a random outcome. They only see the perfect correlation after they compare notes. Classically, like over the phone.
So relativity is safe, but the weirdness remains.
Absolutely. The philosophical weirdness is still there.
And Einstein, to avoid this non-locality, he preferred the hidden variables idea, like socks in envelopes.
Exactly. He thought the properties must be predetermined, like knowing one sock is pink and the other green, even before you open the envelopes. Local, predetermined reality.
But Niels Bohr had a completely different take.
Radically different. Bohr basically said, the properties don't exist until you measure them. The measurement creates the outcome. The two particles are one indivisible system until you interact with it.
Wow. So a total philosophical standoff.
For decades, yes. It seemed like you couldn't experimentally decide between them.
Until John Stuart Bell, 1964.
Yes, Bell. This was brilliant. He took the core assumptions of Einstein's view, local realism, meaning properties are real and local, and turned them into a mathematical inequality, a testable prediction.
Bell's inequality, it set a limit, right? A maximum amount of correlation you could get if the world worked the way Einstein thought, like a value of 2 or less for the CHSH version.
Precisely. Any local hidden variable theory had to obey that limit. But crucially, quantum mechanics predicted you could violate that inequality under certain conditions, get correlations stronger than 2, up to about 2.828.
So suddenly it wasn't just philosophy, it was physics. You could do an experiment.
Exactly. Nature could tell us who was right.
And then Elaine Aspect and his team in the early 80s actually did it.
They did. And their experiments were incredibly sophisticated, designed to close loopholes. The key thing was using these super fast switches for the measurement settings.
While the particles were already flying apart.
Yes. The settings were changed in about 10 nanoseconds, faster than light could travel between the detectors, which took maybe 40 nanoseconds. So there was no way the particles could coordinate using some hidden light speed signal.
Okay, the moment of truth. Did the results respect Einstein's limit, or did they violate it?
They violated it, clearly, significantly. The results matched the predictions of quantum mechanics almost perfectly. Local hidden variables were ruled out.
An aspect clauser, Zeilinger, got the Nobel Prize for this in 2022.
Deservedly so. Their work fundamentally changed our understanding of reality.
So, this means the universe is non-local. Einstein's spooky action is real.
That's what the experiments tell us. At a fundamental level, reality isn't locally contained in the way our classical intuition expects. There's a deeper, non-local connection. It's mind-bending.
Okay, so entanglement isn't just a weird footnote anymore. It's a real thing, a resource. But what is it in, like, practical terms?
Well, mathematically, you describe an entangled state as something you can't separate into independent parts. The system is a whole. Knowing everything about the whole state doesn't mean you know everything about the individual parts until you measure.
Like those Bell states, you measure one qubit, you instantly know the other.
Exactly. Their fates are linked. But it's crucial to remember it's not like the socks.
Right, not predetermined.
No. Before measurement, the individual particles don't have definite properties. They're in a superposition, a blur of possibilities. The definite, correlated outcome only snaps into existence for the whole system when you measure. It's a potential that becomes real through interaction.
And this correlation is stronger than anything classical.
Much stronger. That's what Bell's theorem proved.
So if it's so useful, how do we actually make it? How do you create entanglement on demand?
The workhorse in quantum computing for this is the CNOT gate. Controlled, not T.
Okay, explain that.
It's a 2-qubit gate. It flips the state of the second qubit, the target, only if the first qubit, the control, is in the 1A state.
Simple enough if they're just worries or 1As, but what if the control is in a superposition?
That's where the magic happens. Let's say you start with 2 qubits, both as 0A, so 0 yoyas. First, you hit the control qubit with a Hadamard gate.
Which puts it in a superposition of 0A and 1A, right? Half and half.
Exactly. So now you have a mix of 0A and Inteno. Then you apply the CNOT gate. The CNOT acts on both parts. The 002 part. Control is 0, so it does nothing, stays 0, okay. The tendero. Control is 1, so it flips the target from 0 to 1, becoming 11A.
So the final state is a mix of 0, 0, and 11A.
Precisely. The state, 0 is plus 11A, a maximally entangled Bell state. The 2 qubits are now perfectly correlated, inseparable.
And that's why these entangling gates are so critical without them.
Without them, a quantum computer is basically just a collection of independent qubits. It loses its power. Entanglement is what weaves them together, creating this huge computational space that allows for quantum parallelism.
Okay, so we can make it. Let's talk applications. Where does this spooky connection actually do something revolutionary? Quantum teleportation sounds like pure sci-fi.
It does, but it's real. It's not teleporting matter, though. It's teleporting a quantum state.
How?
Alice and Bob share an entangled pair beforehand. Alice takes the qubit whose state she wants to send and performs a joint measurement on it and her half of the entangled pair. That measurement gives her 2 classical bits of information. She sends those 2 bits, just regular bits, to Bob over a normal channel.
Like email?
Sure, or phone, whatever. Bob then uses those 2 bits to know which specific quantum gate to apply to his half of the entangled pair. And when he does that,
His qubit becomes identical to Alice's original qubit.
exactly. The original state is destroyed on Alice's side and perfectly reconstructed on Bob's. It's amazing. No faster than light communication, because Alice had to send those classical bits.
Still amazing.
Yeah.
What about security? Quantum cryptography?
Yeah, this is a big one. The E91 protocol by Arthur Eckert uses entanglement directly. Alice and Bob get particles from an entangled source.
Okay.
They both measure their particles randomly, choosing different measurement settings. Then they talk publicly, just comparing which settings they use, not the results.
And they keep the results only when their settings match.
Right. Those matching results form a shared secret key. And here's the security part. If an eavesdropper, Eve, tries to measure the particles in transit,
She disturbs the entanglement.
exactly, she breaks the perfect correlation. Alice and Bob can check this by sacrificing a small part of their key data and running a Bell test on it. If the correlation isn't strong enough, they know Eve was there, and they just throw away the key.
So entanglement itself is the security guard.
Wow. The laws of physics guarantee the security, not just mathematical difficulty.
And then there's quantum sensing, making measurements better.
Much better, potentially. Normally, if you use n probes for a measurement, your precision gets better as the square root of n. That's the standard quantum limit.
Okay.
But if you use n-entangled probes, like in special GHZ or Noonan states, they act like one big quantum object. The precision can then scale directly within the Heisenberg limit.
So a much bigger improvement in sensitivity.
Potentially, yes. This could mean things like detecting fainter gravitational waves, building way more accurate atomic clocks, better medical imaging, maybe even navigation without GPS.
But the real powerhouse application, the one everyone talks about, is quantum computing algorithms.
Absolutely. Entanglement is the engine here. Take Shor's algorithm for factoring large numbers.
The one that threatens current encryption.
That's the one. It uses entanglement on a massive scale to link registers together, encoding the answer, the period of a function related to the factors into the correlations of this huge entangled state. A quantum Fourier transform then pulls out the answer efficiently.
And Grover's algorithm for search.
Also relies heavily on entanglement. It starts with all possible answers in entangled superposition. Then it uses operations that collectively amplify the probability of the correct answer across the whole entangled state. It gives a quadratic speed up over classical search.
So in both cases, entanglement isn't just happening in the background. It's the structure enabling the speed up.
It's the absolute fabric. It allows the quantum computer to access and manipulate information in that exponentially large Hilbert space in a way classical computers just can't.
But there's always a but, isn't there? This amazing power, entanglement, is also super fragile.
That's the major challenge, yes. Quantum decoherence.
What is that exactly?
It's basically the quantum system losing its quantumness because it inevitably interacts with its environment, stray heat, magnetic fields, anything. And, ironically, decoherence itself is caused by entanglement.
Wait, entanglement causes the problem.
Unwanted entanglement, yes. The qubits you care about become entangled with the environment, and their delicate quantum state, including the entanglement between them, leaks out, gets lost in the environment's complexity.
And this happens differently for different types of qubits.
Right. Superconducting qubits are sensitive to tiny energy fluctuations and material defects. Trapped ions can get nudged by stray electric fields or heat up. Each platform has its own environmental demons to fight.
So if you can't perfectly isolate them, how do you protect the quantum information?
That's where quantum error correction, or QEC, comes in. It's a brilliant set of ideas.
How does it work? Is it like classical error correction?
Similar principle use redundancy, but it's much trickier with quantum states. You encode the information of one logical qubit across many physical qubits using specific, highly entangled states.
Spreading the information out so a local error doesn't kill it.
Exactly. And you use extra ancillary qubits to cleverly measure what kind of error occurred on the physical qubits, like a bit flip or a phase flip, without actually measuring and thus destroying the logical qubit state itself.
That's really clever. You figure out the error without looking at the data.
Precisely. Then you can apply a correction. Things like the Shor code or the surface code are ways to structure this entanglement to protect the logical information.
So it's like using carefully constructed entanglement to fight off the damaging random entanglement from the environment.
That's a great way to think about it, fighting entanglement with entanglement.
So where are we now with all this? You hear about quantum computers with more and more qubits.
We're in what's called the NISQ era, noisy intermediate scale quantum. We have, tens to maybe a few hundred qubits, but they're noisy, meaning decoherence and gate errors limit how complex the computations can be.
So quantity isn't everything.
Not at all. The big focus shift recently, say 2024 into 2025, has been toward quality. Better qubits, better gates, lower error rates.
And the ultimate goal is the fault-tolerant logical qubit built using QEC.
That's the holy grail. And we've seen real progress. Groups are now demonstrating logical qubits that actually have lower error rates than the physical qubits they're made from. That's a huge milestone.
But the cost is high.
Oh, the overhead is enormous right now. You might need hundreds, maybe even 1,000 physical qubits just to make one high-quality logical qubit. There's still a long way to go for large-scale fault tolerance.
What other trends are shaping the field?
We're seeing more hardware specialization building machines tailored for certain problems. Quantum networking is growing, linking smaller, high-quality processors together using entanglement. And there's a huge effort in software to make these machines easier to use, plus, significant investment pouring in.
Okay, so we've gone from Einstein being deeply uncomfortable with spooky action
To Bell proving it's real, aspect confirming it experimentally.
to understanding how to create with things like CNOT gates and seeing its potential in teleportation, crypto, sensing, and these powerful algorithms.
And while decoherence is a massive hurdle, QEC shows incredible ingenuity, using entanglement's own rules to protect itself.
It feels like the whole story hinges on mastering this one phenomenon. generating it, controlling it, protecting it.
That really is the core challenge and the key determinant of progress, yes.
So as we wrap up, here's something to think about. Entanglement reveals a deep, fundamental interconnectedness in the universe. If this spooky action is real, what aspects of your world, things you maybe think of as totally separate, might actually be linked in ways we just don't see yet? How might harnessing this profound connection change things in the future, maybe in ways we can't even imagine right now?